for the quiz from last time. I'm not going to be able to hand it back to you because I already cut all your names off the top and submitted them to the department. So, but I did register your grades in Canvas. And remember I said the minimum grade you would get is a 70. And then I added up to 10 points on your exam grade depending on what you did. So if you have any questions about how I arrived at that grade, just come talk to me. All right? Yes? Okay, so in the grade book, what happened was I had brought that over from a previous semester's grade book where I had a take-home exam. So it showed up in there, but on the syllabus, I never put take-home exam, right? So basically, it shouldn't have been there. It's kind of like, you know, I start off the semester, maybe I put 9 quizzes in there. We may or may not get to 9. That kind of carried over, so yeah. All right. What are we doing? Guess Heidi's not here today. She left her umbrella last time, so I kept it for her. So I'll take it back. Anybody want to buy an umbrella? No. Okay. So we were talking about antiderivatives last time, right? Talking about antiderivatives. So really been trying to go back and forth of how I want to go about today. And I think what I'm going to do is I'm going to do maybe 1 or 2 more problems related to what we did last time. Then I'd like to introduce you to this new thing. All right? So let's take a look at a problem like this. Did anybody recognize number 4 on the quiz as a homework problem? It was a homework problem, except I added a cosine x on the outside, but yeah. All right, so let's take a look at this. Let's start by just making sure we understand what the heck is going on here. All right, so I'm giving you a function here. I want us to find the general antiderivative. All right, so find the general antiderivative. Now, you see 2 terms, right? So if you see 2 terms, you can do them individually. And each of these is x to a power, right? X to a power, x to a power. So we have that rule that we developed in class last time, which, by the way, that rule is on your formula sheets. Okay, but you have to kind of flip through, and I'll show you where it is later, okay? But it's there, so you don't have to necessarily memorize it. For the final, you don't have to memorize it as long as you know where it is on your sheet. So what about these constants that are in front? They just come with us, right, when we do our antiderivative? So I'm going to start by doing 5, and then how do I get the antiderivative of this? So I go 1 over whatever the power is plus 1, right? So 1 over 4, and this will be multiplication. 1 over 4 x to the 4th power. So I'm using this rule that if you have x to the n, the antiderivative is 1 over n plus 1, x to the n plus 1. That's how you get your antiderivative, right? That was the formula we came up with last class, and then plus a constant, right? And this formula worked except when n was -1, but then that was that special case. That was natural log. So that's this, and then plus we have the 7, and then we have times. Now what's n here for us? What is n? 1/4. So we're going to have to add 1 to 1/4, aren't we? So if I take 1/4 and I add 1, that's the same as doing, that's the same as doing 1/4 plus 4 over 4. So you just convert the 1 into same denominator, and that's going to be 5/4. Get used to this because you'll be doing this a lot. Just like in this class, you have to subtract 1 a lot. Here, Cal 2, you have to add 1 a lot. So 5/4, right? Yeah, so in the beginning, when I do this, I'm supposed to do 1 over 5/4, right? If this is a fraction down here, this is always going to flip over, isn't it? So it's always going to be the reciprocal of that. But I'm going to write it this way just to start. And then I have times x to what power? That 5/4. And then I'm done, but I have to add a constant. And now I want to just clean things up. So 5 times a fourth is 5/4, x to the fourth, plus, let's see here, if I flip this over, this is going to be 7 times 4/5, right? And then I can multiply the 7 times the 4 to get 28, and 28/5. So 28/5, x to the 5/4, plus some constant. And that right there is our general antiderivative. Right, so I was hoping that today you would come in having looked at a few of the homework problems and felt comfortable with this. All right? So now I'm going to proceed. I'm going to give you something that looks a little different than this. Let's see how we deal with it. Any questions on that though? Before I erase it? All right. Okay, so how about this? Square root of x minus 3x plus 7 over x squared. Now, your intuition might be telling you that, okay, I can find the antiderivative of that because that's x to a power. This is negative 3 times x to a power. You can find the antiderivative of that. How about the antiderivative of 7? Sure, right? 7x. And then the antiderivative of x squared, you can find that, right? It's 1/3 x cubed. So individually, you can find the antiderivatives of each piece. The problem is we can't do it that way. Why can't we do it that way? Because it's a quotient, right? This is division. And so we saw last class that I gave you an example where I gave you a multiplication, and I said you can't just go backwards because if you took the derivative to check it, you would have to use a product rule. Same thing here. If we just do these individually and put our answer together as a fraction, then when we take its derivative, we have to do quotient rule. And it will not come back to be this. So because of the division, we are kind of stuck. Except there's something really nice we can do that has nothing to do with calculus, that just has to do with algebra. And that is, we can split this up into 3 fractions, right? We're allowed to do that? So long as you have a single term on the bottom, right? And multiple terms on the top, you can split it up. Now, if you have multiple terms on the bottom and 1 term on the top, you cannot split it, right? It has to look like this. So we got lucky that we can do that. And then I'm going to clean things up. So I'm not taking any derivatives yet, all right? Or sorry, antiderivatives. I'm just rewriting the problem. Okay, the only thing I did on that step was converted my square root into x to the 1/2. And now for this, I'm just going to use property of exponents. To put those together, I take 1/2 and I subtract 2, right? So I subtract the exponents. What's 1/2 take away 2? 2, that's the same thing as we get a common denominator, right? So 4/2 like that. So negative 3/2. So this becomes x to the negative 3/2. What does this one become? 3 just over x, like one of the x's cancels. So you have a choice here. You can either write this as 3 over x, or you can write it as 3 times x to the negative 1. It's your choice. Which way do you want to write it? Negative 1, why? Because it's all on the top, and then you can use this formula. But wait, this formula doesn't work for negative 1, right? Right? So this is that one case where you have to be careful. I am aware, at this point in time, I am aware that this is going to become like a 1 over x. Do you see that? So I'm going to write this next one as 3 times 1 over x. And I'm going to leave it that way because I have now memorized, burned into my brain, that the antiderivative of 1 over x is the natural log of x. Okay? It's burned in. Okay, this one, what about that? 7 over x squared. That is not the special case. In this one, we do want to move it up. So we will just write this as 7x to the negative 2. Okay, so I can use that formula for this one, and then I can use that formula here for this one. But on this one, I have to just know and memorize that. Yes?
So for that one, you can't use the formula because it would be negative 1 plus 1?
Because we'd have negative 1 plus 1 down here, which would give us 0, and 1 divided by 0 is undefined. So our formula breaks down. Okay, you ready? Now we're ready to actually take the antiderivative. We haven't done any calculus yet. All right, so here we go. The capital F, the antiderivative of this, should be, okay, for this one, here's our n, right? So I need to add 1 to that. So if you add 1 to negative 3 halves, you should get negative 1/2. Do I have to keep showing that, or you're okay? Negative 3 halves plus 1 is negative 1/2. So it'll be 1 over negative 1/2 x to the negative 1/2. So this is your 1 over n plus 1 x to the n plus 1. Got it? All right. Next one, minus, the 3 comes along, and then what's the antiderivative of this? We just said natural log of x. And I said last class, when you do the antiderivative, make sure you put that x in absolute values. And then this next one, plus 7, 7 will come along. And then this time, n is negative 2. So you take negative 2, you add 1, which is negative 1. So times 1 over negative 1 x to the raised to the, you're adding 1, right? So negative 1. And then don't forget the plus c. Yes or no? I mean, I'm not sure if the looks on your face is that you're ready for this to be done, or I'm not showing the arithmetic of adding those numbers, but yes, yes, yes? Yeah? Okay, so what part? This?
Yeah.
Okay, so let me do this one right here. If I have x to negative 2, and I want to find the antiderivative here, this is my n. And I'm going to use the formula 1 over n plus 1, x to the n plus 1, right? So n is negative 2. So let's just write this formula. 1 over n here is negative 2 plus 1, right? X to the negative 2 plus 1. So this is 1 over negative 1, x to the negative 1. That's this. Got it? Okay. All right, so I did the same thing on this one. That's how I got this. All right, let's clean this up. So this is, what does this become? Flips negative 2. Negative 2, x to the negative 1/2. And then here we can just leave it, negative 3 natural log of x. And then here, this is just going to become negative 1, right? So I'll just put it in front of the 7, negative 7, and then x to the negative 1, and then plus c. And I can box this up. Another version, hold on, Chris, another version that you could see of this answer, like if you look in the back of the book, you might see this. So if you look in the back of the book and you see that, do you understand where that came from? They dropped this down, right? Negative exponent, they dropped it down, and then x to the positive 1/2 means the square root. And then here they dropped that x down underneath the 7, and then this they left it alone. Okay? Either one of these, they're both correct. Sometimes we want to leave it like this because, well, maybe we want to do the antiderivative again. You know how we did like first derivative, second derivative, third derivative? Maybe we want to do the antiderivative more than once. We won't do it here, but we could, theoretically. And you'd want to leave it in this form because you have your n's right there, right? Okay. Yes, now, Chris. Where? Here? This right here. It flips. So you're taking 1. Just look at the top as being 1 over 1. And the bottom is negative 1 over 2. So when you flip this, it comes 2 here, negative 1 on the bottom, multiplication. Go across. Negative 2 over negative 1 is negative 2. I mean, sorry, 2 over negative 1 is negative 2.
So it doesn't cancel with the 2 over 1?
Where?
So in my head, I was thinking that you just put the 1/2 on top right?
Just move it up
No,
top?
no, no. Power,
Here.
power. That to the 1, so like where the 1 is at?
Here? I'm not taking a derivative though. How did I get to this? I took the antiderivative of this, right? This is x to the n. So I used the formula. The formula gave me 1 over, this is n plus 1. This is negative 3 halves plus 1. X, this is negative 3 halves plus 1. So once I'm here, I'm not doing any more derivatives. I'm just cleaning up the answer. I'm just algebraically like, what is that? That's negative 2.
Oh, okay, I was thinking that.
You're trying to do the derivative or something? Yeah.
So this was the second derivative.
Say again? What?
If this was the second derivative, it's cx plus d, right?
Okay, so if we wanted to do another antiderivative, we would have to figure out what's the antiderivative of c. And that would be cx plus d, but I'm not talking about that. Yeah. Okay, I have a new one for you. You ready? Start off with baby steps here. You know what? No. Yeah. I like that. I want to know the antiderivative of this. All right, so things just got serious, okay? All the little easy formulas are no longer applicable. Do you see x like x to a power by itself? Like in the previous problem, we had to split it up, but each one of those was like a number in front of x to a power, and we can handle that. But this is, multiplication. If I asked you to take the derivative of that, that would be pretty bad, right? You'd have to do product rule. Now I'm asking you to go backwards and try and figure out what function this came from, right? What function do you take derivative of to get this? And there's nothing really that you can do, all right? So this is where we start to learn our first method, our first sort of attack that we use on these things, all right? So it is called U substitution. Okay, it's called U substitution. You might also hear people call it U sub, or you just might hear people call it substitution. All right, it's all common language that we use. So here's the idea behind substitution, all right? What I want you to do is I want you to look at this thing here, and I want you to tell me if you can identify anything in here. Look for something, okay? Look for something, and see if its derivative is also in there. So does anyone see something in there and its derivative is also in there? What, say again?
I said 2x.
You said 2x is what? The derivative of x squared plus 1. Does everyone see that? That if you look at this right here, the derivative of x squared plus 1 is actually 2x, right? That's the basis for what substitution is about. What you're looking for is something, and you're hoping to also see its derivative within the problem, all right? So U substitution. Look for something, okay? I don't know what else to call it. Look for something and its derivative. Its derivative. Okay, so you have to go do that first. We all agree that x squared plus 1 is the something here, right? And its derivative is sitting there also, which is 2x, yes? All right, so now what we're going to do is we are going to make a substitution. Okay, I'm about to make a substitution. So I'm not ready for this capital F yet. I'm just going to make a substitution right now. I'm going to say let u be equal to x squared plus 1. All right? So anywhere I see an x squared plus 1, I'm going to replace it with u. Also, I know that the derivative of u is equal to 2x. Do you buy that? Like if I take the derivative on both sides, the derivative of this should be 2x. Yes? So let's rewrite this problem then. This problem actually becomes what? Yeah, so this is going to be a little weird, but what does this become? Cosine. I'm going to write that first, okay? This is cosine of u, right? And then this piece right here is the derivative of u, right? du. I know that looks strange, but this gives us an idea of where we should go with this, right? So I'm going to give you a slightly more formal way of presenting this to you. I just wanted to kind of get you to think about this first. So by rewriting this, by making a substitution and rewriting this, this right here should give us some indication as to how to get the antiderivative. If I ask you right now, if you ignore that du right now, and I ask you right now, what's the antiderivative of cosine of u, what would you tell me? Sine of u, right? The antiderivative? So maybe, question mark, maybe the antiderivative of this thing is sine of u. Maybe. Plus a constant. Now what was u? X squared plus 1. Let's just try it. Does that work? Sine of x squared plus 1 plus a constant. Does this work? Take the derivative of this. So constant's going to go away when you take derivative. What's derivative of sine of something? Cosine of it, right? So you'd have cosine of x squared plus 1 times, then the chain rule would say derivative of what's inside, which is 2x. And that's where the 2x comes from. Y'all kind of follow that? Okay, so this is where we're going to head, all right? We're going to want to do more of these problems. But before I can do it, I need to introduce some new notation. And the new notation that we're going to use is going to help us keep track of like what the hell this is and stuff. So, notation time. Okay, we're all familiar with if someone gave you a function and asked you to take the derivative, we all know the different notations for that, right? Like f prime, take the derivative. You could do like, d dx or something like that. It means take the derivative. But what's the notation we use to tell somebody to take the antiderivative, right? What's the notation? So here's what it is. So given some function f, then this symbol, which is like an S that's been stretched out, okay, with f of x written next to it, and then next to that you write dx. This right here is the notation we use, and that notation means find the general antiderivative. So from now on, when I want you to find the general antiderivative of something, what I'm going to do is I'm going to write this symbol, I'm going to put the function right here, and then I'm going to just slap a dx to the outside. Now I know right now you might be saying, what's the dx? For us, the dx means like the derivative of x, and that's always been a 1, right? Hasn't dx always been 1? So this is really a 1, but I'm not going to write 1. I'm just going to write dx. And you just understand that it's 1, okay? So these symbols this whole thing has some names to it. This right here is called the integral sign. the function itself, the thing you're trying to find the antiderivative of, is called the integrand. And this little dx right here is called the differential. So I'm telling you, don't worry yourself too much about the differential. Just focus your attention on the function that we're trying to find the antiderivative of, and that symbol is telling you, go find the antiderivative, all right? Now the symbol comes from something else, and if any of you take me for Cal 2, I'll explain where the symbol comes from. We'll go into it in more depth. Hopefully if you take Cal 2 with someone else, they'll do that also. But I'm going to, for right now, just leave that symbol alone, all right? So this question right here, I'm going to repose it, all right? I want us to run through this problem again. And I think you're going to see how, hopefully you will see how this notation that we're going to use is going to work better now. Okay, so here's this problem. And I want to tell you that I want you to find the antiderivative. So I'm going to put this symbol in front of it. And I'm going to slap dx to the outside. Okay, so now that means go find the antiderivative of that function. All right, now we had already recognized that there was a substitution we could make that u was equal to x squared plus 1, right? And now I said take the derivative, right, on both sides. This time I'm going to be a little bit more precise with my notation. I want you to take the derivative on both sides of this with respect to x. In other words, the left side becomes du dx, and the right side, the derivative with respect to x of this is just 2x. Right? Derivative of x squared is just 2x, derivative of 1 is 0. Now, one additional step. I'd like to get that dx over here. So I'm going to multiply both sides by dx. Okay, y'all with me? Now, if you notice, this is critically important at this point that you notice this. This right here, that's u, right? That's u. And then do you see that 2x dx? I could, if I want, slide that 2x right there next to the dx, and they would be right next to one another, wouldn't they? Because it's all multiplication there. So do you agree that what's in red matches up exactly with what I have here? So now all I'm going to do is just replace everything. Okay, so I'm going to now rewrite the integral. And you know what I think I'll do? I'll go ahead and do that step since this is our first problem. I'm going to rewrite this. So I went ahead and slid that 2x over here, okay? And now rewrite the entire integral in terms of u. So the antiderivative of cosine of u du, all right? So what we've done is we transformed this problem into this problem, right? By making a substitution, we have a new integral that I think is easier for us to do, because this is telling you to find the antiderivative of cosine of u, right? That's what it's telling you, and we said that was sine u. So this should just be sine u plus a constant. But you can't box this as your answer because your answer has u in it, right? So you got to get u back to where it came from. U is x squared plus 1 plus c, and that's what we had before. Okay, do y'all see how that notation flows? I have a question? Yes.
What happened to the du?
What happened to the du? Excellent question. There's multiple ways to look at this. The way I want you to see it, what is this symbol telling you to do? Find the antiderivative. This right here is what you want to find the antiderivative of, right? This right here keeps track of what your variable is in the problem, all right? The variable in our problem right now is u, right? Over here, what was our variable? X. So don't look at this as something that has to become something over here. It's like just right there, okay? And then find the antiderivative of that. So this is purely just notation to keep track of things. Is that okay with you? Now some people don't like that. So I'll just tell them, look, if you need du to become something, then make the du become the c. All right? It's not what's happening, but if you really just need to know what happens to that, just say that's where you get plus c from. Then maybe you won't forget the plus c. All right, that was the first like baby problem. All right, you ready for something a little bit harder? Yes? Okay, how about this one? Yeah, we can do that. Okay, so you have nothing else in your arsenal. You've got the power rule, right? Which is the 1 over n plus 1, x to the n plus 1 that we did last class. You have things like you've memorized that the antiderivative of cosine is sine, that the antiderivative of sine is negative sine, that the antiderivative of secant squared is tangent. All these things that you brought from Cal 1 that you had memorized, you know them backwards, right? I'm saying right, like in theory you do, okay? But this right here, you can't do it. There's nothing that we did that you memorized that would take us backwards from here, right? So since you have nothing else, the only other tool you have at this point is this thing called substitution, which means you have to be able to see something in there and its derivative. So does anyone see the something? What do you see? The natural log of the square root of x? Okay, let's try this. Let's see. If u is equal to the natural log of the square root of x, I'm thinking through what you're thinking here, then the derivative of that, what's the derivative of that? 1 over the square root of x times 1 over 2 root x, right? Oh yeah, du dx, sorry. Okay, so I agree, I do see this. I see that, there it is, it's right there, okay? So imagine now that this is no longer in play, all right? Look at the derivative though. Do you see that derivative here? I see just a root x. That derivative has a root x and a 2 root x in the denominator, doesn't it? This seems like it's too much, right? Like this down here is too much. It's like you went looking for a u. It's like you grabbed too much of the function because it's spitting out something that is more than what we had left. Do y'all all see that?
So u is the square root of x.
So you want to try something different? U is square root of x instead? Okay, so let's try that. U is the square root of x. Okay, what's the derivative of u with respect to x? 1 over 2 root x, right? Okay, so I'm going to now bring the dx over. Du is equal to 1 over 2 root x dx. It's still too much. Why? Because we have a 2 here, right? It's okay though. So just watch. I want to make sure everyone's good up to this point. What I'd like to do first, I'd like to rewrite this because I know some of you are having trouble seeing this. But this is the same as this, right? I tried to sell your umbrella. Nobody wanted it. Yep. Okay, is that the same? Is this the same as this? Yeah, it's multiplication, right? So what I did is I left this here. I peeled the root x out the bottom, and it's just that, right? You all see that? So if I were to look at this substitution right now, I'm going to be able to replace this with u, right? This with u. And then, I have a problem, don't I? This right here is 1 over root x dx. I don't have 1 over root x dx. I have 1 over 2 root x dx. What could you do to this to make it that? What could I do to this to make it this? Look, I have an equation here, right? What's the problem? What is throwing things off right now? The 2. How could I get rid of a 2 over here? Multiply both sides by 2. Right? So if I multiply this side by 2, I get 2 du, right? If I multiply this side by 2, they cancel. And so do you see now that this side of the equation is exactly what's in red there? Y'all see it? And this square root of x is going to go into the natural log. So I'm going to rewrite the problem now. This becomes integral natural log of u times, what is all that? 2 du times 2 du. I'm going to go one more step. 2 integral natural log of u du. Right? Is it okay that I took the 2 out here? Sure, because remember, the 2 is always going to come from the right, isn't it? So we know when we take the antiderivative, whatever the antiderivative of this is, I will just multiply it by 2. How does this feel to you all? I'm not quite sure how to read your faces right now. It's a little concerning. Only constants can come out. Nothing with u or nothing with x can ever come out of an integral. So now you're left with this. Can you find the antiderivative of natural log of u? Can you find the antiderivative of that? Now you can find the derivative. The derivative of that you know. But do you know its antiderivative? And you don't, do you? So I want you to look on, now's the time I want you to break out your formula sheets if you have them. Can I borrow yours real quick? I want to tell you what reference page this is. Reference page 6. Okay? And you'll see that reference page 6 has the little integral sign. Do you see it? And I want you to start at formula 1. Formula 1, skip it, because that's later. Formula 2, do you recognize formula 2? That is the power rule. That is but they're using u instead of x, right? Do you see anywhere in formulas 1 through 20, 1 through 20, anywhere there, do you see the antiderivative of the natural log of u? Do you? No. 3 is you need the natural log in here, in the integral. See, formula 3 is this. Formula 3 is this formula. What's the antiderivative of 1 over u? Natural log of u, because it's like 1 over x, right? So you should be telling me no, there is no formula, right? So I'm going to allow you to add it to the sheet, all right? It's not on there, but I want you to put it there because it does come up later. So the antiderivative, we'll do it over separately here. The antiderivative of natural log of u is equal to u natural log of u minus u plus c. Do you believe that that's the antiderivative? Could you check it? How could you check it? Take the derivative. So let's take derivative of this. Now just remember, u is like x, right? So how would I take derivative of this piece right here? Product rule. So if I did product rule right here, I have derivative of this, which would be 1 times this, plus derivative of natural log of u. 1 over u times u, right? Okay, and then minus derivative of u, which is 1. With me? Okay, this is natural log u. This is what? Plus 1 minus 1 natural log u. Okay? So what?
Does that element you have to be absolute value?
It doesn't have to be, because here we assume that the u we're plugging in will make the natural log defined. Okay, when you have the 1 over x like you're talking about, you have to put absolute value because it could be possible that x is negative. All right, so this, you can write that on your formula sheet, but let's go back over here now. This should be equal to 2, okay, the 2 comes along, and then this answer, right? So I'm putting in parentheses u, natural log u, minus u, and then plus c. Do you think that I should have put that c inside here? Or do you think it matters? If I put that c inside, that 2 would come through and hit the c, right? And it would be 2 times c. But c is a constant anyway. Twice a constant is still a constant. So it doesn't matter where this c is as long as it's out here on the outside. So this is our answer, but we're not done. Why not? Yeah, because what's u, right? What was u? The square root of x, right? I erased it, but u is the square root of x. So I've got to rewrite this. This is 2 parentheses square root of x times natural log of the square root of x minus the square root of x plus c. This is the antiderivative of this. So if I take the derivative of that, I should get that. What's in here? I should get that. Does this seem like it's getting somewhat complicated pretty quickly here, or no? All right, let's do another one. How about this one? First thing we do is make sure we can't do this like with any of our little things we've memorized, or x to the power, we can't, right? It's pretty evident just from the beginning we can't do anything like that. Okay, so the only thing you have at this point, the only thing you've got is substitution. So at this point, you need to see something in its derivative. So what do y'all see? So look, here's the deal. You're about to, most of you, I think all of you are probably going to be going into Cal 2. You have to be ready to step up to the plate and take a swing and miss. Okay, I've told you this already. You have to prepare yourself to try and fail and try and fail and try and fail, and then it will start to come. But if you're hesitant and you're not willing to take the swing, you are never going to get good at this, all right? So you must, at this point, try and see just go for it. Just give me a U, and then we'll figure out whether or not it was a good U or a bad U, all right? But there's nothing to feel bad about if it's wrong. And then as you do more, you will start to be able to pick the U's correctly, all right? Okay, sign what? Sign, who said that? Terrible. Who did that? No, I'm kidding. Sign X, right? Let's go for it. It's fine with me, right? Because what's the derivative of sine of X? Cosine X. And do you see cosine X in there? Yeah. Okay, so that's a start, right? The derivative of this with respect to X is equal to cosine X. Now, we have a problem. We have a problem. The problem is that the cosine x that we see, do you see that the cosine x is in the denominator? Do you see that? That can't happen, right? So this is a new little like rule. Whatever you pick for u, whatever its derivative is, can never be in the denominator or trapped inside of a square root or anything raised to a power. The du part, this piece right here, must be able to be slid out and pushed to the side, okay? So do you see this cosine x right now? It's being squared and then add 1, it's in the denominator. There's no way you could just take that cosine x and slap it out here. Do y'all see that? So that choice, although I do see sine, I do see cosine, the fact that this du part is trapped makes me say no. I'm going to try something else, all right? So let's try something else. Okay, how about cosine x this time? Okay, well, if we do cosine x, what's the derivative with respect to x of cosine x? Negative sine x, right? Now, I don't have negative sine x. I have positive sine x, but that should be okay because a little while ago we were off by 2, weren't we? And we just doubled both sides. So if I'm off by a sine, I should be able to like multiply both sides by -1 and also be able to deal with it. So it's okay to be off by a sine. It's okay to be off by a multiple. Say that again. When you pick u and you're looking at its derivative, it is okay for it to be off by a sine. It is okay for it to be off by some constant. But it cannot be trapped in the denominator or trapped in anything that it cannot be factored out, slid out to the side. Can the sine x part be slid out to the side? Absolutely. Let me rewrite the problem so you can see it. If I rewrite this, that's what I have, right? See that sine x would just come off the top and slide out to the side, right? Now this over here, the next step here is to just move that dx to the other side. So I multiply both sides by dx. I'm going to do that every single time I do substitution. I'm always going to bring that dx over here. So do you see that I'm trying to get this thing to match up? It's almost like I'm trying to like get this puzzle to work. I need sine x dx, right? I've got it right there, but I got that negative sign. So I'm almost there, and then I also have the cosine x part right there is this. Okay? So how do I make these red ones match? What do I do here? Move the negative over there. How do I do that though? I mean, technically I'm doing what? Divide by -1 or multiply by -1, however you want to look at it. So this is going to become minus and this is going to become plus. So now they match, right? This matches with this. I replace this with u, and I should at this point be able to rewrite the integral. 1 over 1 plus. Yeah, be real careful here. Cosine x squared means you're squaring the cosine, right? So if I'm replacing cosine with u, this becomes u squared, right? And then this right here is times, what is that? For us, it's what? Negative du. So that negative is kind of weird, right? Negative, because it makes it look like I'm going to subtract. But I'm not going to do that. I'm going to put du here. And I'm just going to make that -1 right there. Do y'all see? I just took that negative that was in front of the du, slid it up there. I'm going to go one more step. This equals negative that. Okay, so we've gotten to this point now, right? As we're sitting here looking at this, the neurons in your brain are firing or not firing. I'm not sure what they're doing. But I'm really hoping that somebody recognizes this. It was something we learned. I told you we took the derivative of it and I said, hey, this comes up a lot in Cal 2. You'll see it a lot in Cal 2, like put a star next to it. It's in your formula sheets, but I'm wondering if anyone recognizes it. Not quite, almost almost.
Inverse tangent.
Inverse tangent, arctangent. The antiderivative of this is inverse tangent. So let me remind you. If I ask you right now to take the derivative of the inverse tangent function, this is 1 over 1 plus x squared. And when we covered that, I put a star next to it. I said, remember that, it's coming up, it's going to be back. It will be popping up in Cal 2 all the time. So here it is. Do y'all see it? We have in here 1 over 1 plus u squared. So the antiderivative of that should be arctangent of u, right? Because we're dealing with u, not x. So this becomes, don't forget the negative out here, negative arctangent of u. That's it. That's the antiderivative of this, plus c. We done? Is that done? Box it up and done? What do I have to do? I got to replace u with what u is, all right? So this is negative arctangent of, what was u? Cosine of x, and then plus c. There it is. So what did I tell you last class the good news was about this? You can always check your answer. So if we were asked to take the derivative of this, we should get that in there, shouldn't we? We should. I'll do it quickly because now we're going into Cal 2, right? So we're all masters at differentiation. I'm okay. Okay, so negative is going to come out here. I'll make it a -1 times the derivative of arctangent of something, chain rule, right? Derivative of arctangent of something is 1 over 1 plus the something squared times, chain rule, the derivative of what's in here, which is negative sine x, and this negative and negative become plus, and you go back to where you came from. Okay? Y'all all right? Okay, let me see here. Can you already see what I was talking about last class where, like in Cal 1, you have like product rule, which is very structured, you know, you have a procedure. And then quotient rule, procedure, chain rule, procedure. Can you already see how this is not so procedural? Like you're going to have to figure out what the u is. Like nobody's going to tell you what it is. You've got to figure it out. Can you see how that's already very different? Okay. And it's very difficult to teach this sort of thing. You don't know where your student is with this. Yes?
Now, when you check this antiderivative and start looking at it, are you going to think of this from a quotient perspective, or are you going to think of this from a log of division, or division of log? So therefore you could create, separate it, do the subtraction.
I don't see a logarithm.
That's what I was asking. It's, when you look at this, like, would this be a quotient thing, or would this be separated through?
So when you're looking at an integral, all right, you are not allowed to just introduce a log, okay? Because then you're no longer trying to find the antiderivative of what you started with. The difference is like this. If you have an equation, in mathematics, you can always do something to both sides. So I could do like natural log here, natural log here. Yes, you're allowed to do that. But if I give you just an expression, let's just say I say x plus 4, and that is not an equation, okay? It's just an expression. You cannot just come in here and take natural log of it and say it's the same thing. So when you have an equation, the solutions to this should be the same as the solutions to this. That you're allowed to do. This is an expression, and so we cannot just come in here and like square the top and bottom or take natural log or take sine. I know what you're getting at. You like C division, you want to split it up into 2 with log, but you're not allowed to just inject the log into this, all right? Yeah, you're trying to figure out, yeah, it's good because you want to think through that. You want to know what you can and can't do. The big thing I see students make mistakes on is they try and like square the top and bottom. You wouldn't want to do it here, but that's something I see students, well, let's just do that. Let's just put a square root here. Just make the problem a little bit more difficult there. Okay, so if I put a square root there, right, you might be tempted to square the top and bottom because you're like, I don't like the root. You can't do that. You're changing the problem. You can square both sides of an equation. That's not an equation, so.
Could you take the antiderivative of each one separately?
Okay, good question. Can you? What do you think? What do you think would happen if you take the antiderivative top, antiderivative bottom separately, and just give me those two antiderivatives? Do you think it's going to work? It's not going to work. Because when you take derivative of that, you have to use the quotient rule. And it's not going to take you back. Look, these two things, okay? These two things right here from Cal 1. Those two things right there, the product and the quotient rule. If, okay, this is a big if, all right? If in some dreamland, some dream world that's not this world, in some dream world, the derivative of this is just the derivative of each one multiplied, and the derivative of a quotient is just the quotient of the derivatives. That's dreamland, okay? If this is the way calculus was, calculus would not be that hard. People would not struggle with it. It's all these rules that make it hard because, especially now, going backwards, we can't just do the antiderivative of the top and bottom. We can't. This comes from something, simplifies to become this, and we know there's got to be products and quotients in the answer, and you can't see it backwards. I'm sorry, you just can't. It's very difficult to see where that came, well, unless you've done a lot of them. Okay, yes?
I think the U is the bottom.
Okay, so are you ready for a U? Yes? Okay, let's go with the process here. Let's look for a U, let's look for its derivative. I made it pretty easy to see or no? What's U? Well, let me work on it. You want me to do the whole bottom or just this? Do you want me to grab the whole root or not? Think about this. If I grab the root and take the whole bottom, okay, then this is no longer here. The derivative of that is going to have a root in it, isn't it? And I don't have any more roots to work with. Do y'all see that? So I don't want the root. Just look for something in its derivative. That's something, right? What's its derivative?
Didn't you say it couldn't be trapped in there?
No, that was
The du can't be trapped. The du can't be trapped. So this guy, it can be anywhere. This one can't be trapped inside something. So what is this? 2x plus 3, right? I forgot my dx over here, right? But I always am going to move it over here, right? So I'm just going to start just putting it here at the end every single time. So I'm not going to write du dx anymore. I'm just going to write du, the derivative, and slap a dx onto the end. Yes?
Can I substitute two things?
Substitute two things at one time?
Like two different steps.
What was the substitution you were thinking of doing? Like what two substitutions?
I'm just asking.
So you would have two letters then?
Yes.
Then my answer is yes and no. I think that has to do...
I see that it's missing a 3 somewhere. Or, hold on. Am I?
Yeah.
Yeah.
You're not doing two substitutions, though.